Yeah, this is Sam's project, and I hope I can do it justice. He might be listening in. He's in an exploration camp in northern British Columbia right now, and it's 4 a.m. for him, but he said he would try. So yeah, this project is really just focused on one deposit, which was already known to be very rich in palladium by porphyry standards. And as was already mentioned in the previous talk, we know that mantle-sourced arc magmas that are gold-rich should be similarly endowed in PGEs. And it's always been kind of a mystery to me where those metals have gone. So we chose this system to look at in detail to see where in this one deposit the platinum and palladium might have gone. And the focus ended up being almost entirely on palladium here because there's not very much platinum in this system. And Sam had a lot to say about that, but I'm just focusing on palladium today. We know that palladium's fluid mobile, and it should be, under some conditions, partitioned from magma into an ore-forming fluid. So that was the basis of this study. And one of the key questions in my mind was, is there potentially a palladium-rich mineralization type that people haven't recognized because the controls on palladium mineralization differ from the controls on gold and copper. So it gets dumped in rocks that don't obviously look mineralized. Since ore grade for PGEs is in the parts per million, you could easily overlook these things. So New Afton, it's a copper, gold, silver, palladium porphyry. It was mined from 1978 till 1991 by Teck in an open pit, and then New Gold took it over, and they've been mining underground since 2012. And the proven and probable resource in 2019 was 1 million ounces of gold and 0.8 billion pounds of copper. And what's unusual about New Afton is that people at New Gold knew from the beginning that there was palladium in their system, and they took the unusual step of assaying for platinum group elements on all of their 2-meter core intervals. So they have a huge legacy database with palladium data that we can use to map out the distribution of palladium in this deposit. And as far as I know, nobody else has ever done that. However, they didn't really have a clear idea of the distribution and occurrence and associations of PGEs because the previous work had been focused on relatively small sample sets. So looking at the deposit geology, these are cross sections showing lithologies in the middle or on the left, alteration in the middle, and mineralization type on the right. In green on the left side is the Nicola volcanics, which are between 238 and 201 million years old. They're not just differentiated on this diagram. They're monomictic and polymictic tuffs, tough breccias, a real mess actually, very hard to divide them up in drill core. And then on the right, separated from those by what is called in the mine environment called the hanging wall fault, is what they call the pickrite, which is also part of the Nicola group. Jacob Hanley has identified these as high K and keramite lavas and intrusives. They may be coeval with mineralization, but the people at the mine are sure that they're quite a bit older. And that's something that might still need to be resolved. Then there's intrusive rocks from the iron mask batholith, including the potassic diorite, which doesn't show up on this section, but will in one of the plans later, and the Cherry Creek monzonite. So now, can I get my pointer going here? Here it is. Sorry, I've forgotten how to get a pointer. Well, can you see I hope you can see my mouse here.
I can.
Okay, good. So this is the Cherry Creek monzonite up in here, and you'll see there's a close spatial association between the monzonite and mineralization. And this here is a copper and gold grade shell, 0.46% copper and 0.4 ppm gold, and there's another little bit of mineralization down here. The alteration associated with the mineralization is potassic. There's K-feldspar dominant potassic alteration in the monzonite, and biotite dominant potassic alteration out here in the Nicola volcanics. And then that's surrounded by and partially overprinted by a phyllic alteration zone, which is this sort of tan colored, and then this propylitic alteration farther out. And the alteration in the pickrite is relatively minor, and it's thought that the hanging wall fault and the properties of the pickrite kind of stop the fluids from moving through that pickrite unit very effectively. Looking here in plan, the spatial distribution of copper and gold, and now also palladium is shown. Sam did a complete wireframe model and did all the kriging and domaining of the deposit for palladium. So he's got a very good view of the distribution of palladium. So the 0.02 ppm palladium shell is this dashed line here, which is very close to the monzonite and parallel to the gold and copper grade shells. And then the 0.1 ppm palladium grade shell is here, the dot dash line that goes around like this. So clear spatial link between palladium, gold, and copper mineralization, which in turn are closely associated with this Cherry Creek monzonite. This is a 3D rendering of the surface and the open pit from the Tex open pit. And the red here is the Cherry Creek monzonite, and the dots are the places where Sam went in and resampled based on the existing PD data. He went in and took samples that looked interesting for having unusually high palladium concentrations or to represent different alteration lithofacies. And then he broke down those 2-meter assay intervals by rock type and by alteration type, try to figure out what was actually controlling palladium distribution and also platinum. And these were all analyzed by lead fire assay at ACT Labs with detection limits of around, I think, 0.1 ppb. So they're quite accurate analyses. And he put all of the data, he did a lot of statistical analysis, and using k-means clustering, he was able to separate 3 statistical groups that are very distinct in terms of platinum, palladium, and gold concentrations. So group 1, group 2, group 3, and the very simple difference is group 1 has both high palladium and high gold, these guys here. Group 2 has high palladium but low gold, so palladium's high, gold is low. And group 3 has both low gold and low palladium. And these turn out to be very distinctive petrologically as well. Oops. The group 1 samples with high palladium and high gold are clearly representative of this biotite altered potassic alteration zone in the hypogene, the primary hypogene ore assemblage of pyrite, chalcopyrite, sometimes with phyllic overprints. But the key thing that sets these apart is that they are all within this primary hypogene copper gold mineralization. And group 2, which has high palladium and low gold, is almost universally associated with older magnetite apatite veins. There's an IOA type vein system associated with this deposit, which apparently is very early. It predates the main hypogene mineralization event. And these magnetite-rich veins appear to have localized palladium deposition for this group 2 set of samples. So they're also associated with quartz carbonate alteration and generally controlled by fault movement, brecciation, which is clearly post primary hypogene. And what seems to be happening here is that this primary magnetite has been partially martitized, that is replaced by hematite, along with the deposition of iron carbonates or iron-rich carbonate minerals in the open space filling in these breccias. And then the group 3 samples are very similar to group 2, except that they don't have the palladium. And the only real difference that Sam could find here that's consistent is that they don't have magnetite anymore. They've been completely martitized. So they're a more oxidizing assemblage than the group 2 samples. And he didn't spend a whole lot of time on group 3 because they don't have palladium in them. And they don't have any platinum group minerals or anything like that. So there seems to be a link here between palladium enrichment in the group 2 samples and this incomplete process of oxidation of magnetite. Now, moving on to obviously the next thing you'd want to look at is the platinum group minerals. And so Sam spent a lot of time on the SEM and the microprobe identifying and analyzing these things. And he found in both group 1 and group 2 a very similar assemblage of platinum group minerals: so myrtillite, isomertillite, tamagamite, cooperite, and some unidentified palladium, antimony, arsenic minerals. In group 1, these minerals occur either within chalcopyrite or along chalcopyrite-pyrite grain boundary. So they're again texturally clearly linked to this primary hypogene mineralizing event. And they're often associated with hesite. We heard about tellurium in the last talk, and there's a clear association here with silver telluride. In the group 2 samples, the platinum group minerals appear almost entirely in these magnetite domains, which have been overprinted by these later secondary fluid alteration event. So the PGMs tend to occur in this partially magnetized magnetite. Again, a clear textural link between this oxidizing overprint and the previously formed magnetite apatite veins. However, when Sam went on the laser probe and analyzed the platinum and palladium and other trace elements in the sulfide minerals, he was able to show that the palladium budget in the group 1 samples is dominated actually by pyrite. And so this little plot here in the upper right shows concentration of nickel in pyrite versus palladium. And you get up to as much as about 30 parts per million palladium and up to the weight percent level of nickel in the pyrite. These are the pyrite grains here. Chalcopyrite contains some palladium, but definitely pyrite is the principal host for palladium in these rocks. And there's a strong correlation between palladium and nickel and palladium and selenium. There's also some cobalt enrichment in some of the earliest pyrite, but we don't have time to discuss that today, and it's probably not relevant to the main story. And something to point out here is that you can detect the nickel in this pyrite even with an electron microprobe or even an SEM. So the fact that the nickel is like a pathfinder for palladium, that might be useful for people who are looking for palladium in systems like this. Sam did a lot of modeling in Geochemist's workbench. He considered the possibility that the mineralizing fluid was a low salinity fluid, like a vapor or a contracted vapor, or a high salinity, a brine essentially, and found basically the same controls. So you don't need to, it doesn't matter which your favorite mineralizing fluid is. The controls on palladium and nickel and pyrite don't seem to depend that much on that. And so first thing to consider here is this reaction between pentlandite, oxygen, sulfur, and the nickel sulfide mineral vaisite, magnetite. At high sulfur fugacity and moderate oxygen fugacity, pentlandite isn't stable. So looking along here at log sulfur fugacity and contoured log oxygen fugacity, you can see you go from hazelwoodite, pentlandite, millerite, vaisite. So at fairly high FS2, the stable nickel sulfide phase would be vaisite instead of pentlandite. If pyrite is forming at the same time, vaisite and pyrite have, they form a solid solution series. And so under conditions of vaisite stability, you'd expect the nickel just to go into pyrite if pyrite is present. The sulfur gas buffer for fluid coming out of a typical arc magma is shown here in this gray area. So a fluid that comes out of that magma might start up here at some high temperature and be buffered to the pyrrhotite, magnetite, pyrite magnetite reaction boundary imposed by the surrounding volcanic rocks, and then cool down along this trend, dropping through the stability limit for the nickel chloride aqueous species that's carrying nickel in the fluid down around 440 degrees to produce this vaisite component dissolved in pyrite. So we would expect to see nickel coming out of solution around that temperature, which is around the same conditions that we also expect to see chalcopyrite being deposited. The palladium is probably carried in solution as a bisulfide complex, and coincidentally, it also probably reaches its limiting solubility in a palladium sulfide component, which would also dissolve in pyrite at about the same temperature. So this would account for the observation that palladium and nickel appear together in pyrite. You see pretty much the same relationships in the brine, and I won't go through it again. And so trying to, skimming over a tremendous amount of modeling that Sam has done. The thing I want to focus on here at the end is the thing that's kind of intriguing, and that is, we know that there's palladium in small concentrations in a number of copper gold porphyries, but there's a lot more palladium in the parental magmas than we see in the deposits. And it's always intrigued me, where might palladium turn up? Are there palladium porphyries out there that don't have copper and gold associated in the palladium ore zone? And so Sam did more work on this and showed that the presence of a very high potassium-sodium ratio in the fluid can change the controls on palladium and copper in a way that might allow this to happen. So he's assumed throughout that the K-feldspar muscovite quartz AHAK buffer has been operative, so your system is equilibrated with feldspar, muscovite, and quartz. If you have a very high potassium activity in the fluid, then the palladium deposition will still obey this dependence on the bisulfide solubility, and you still get deposition of palladium under conditions similar to what we saw before, around 440, 420 degrees. But the deposition of copper is impaired by this very high potassium activity, so that there will be quite a big temperature range between the conditions where palladium is deposited and the conditions where copper is deposited in a very potassium-rich system. So it may well be that the most potassic alkalic porphyries have an inner shell of palladium-rich pyrite, which is not visibly mineralized with copper, and therefore would never get assayed for palladium. Last thing to talk about is the secondary mobilization of palladium. What caused palladium to move into those group 2 veins, which are clearly cross-cutting the hypogene mineralization? And why is that assemblage the same as in the group 1 mineralization? And what Sam has proposed is that a late oxidizing reactive fluid that contained tellurium, mercury, arsenic, and antimony came through and broke down that early nickel palladium bearing pyrite and therefore liberated palladium into solution. At low water rock ratios, the palladium won't get far, but it'll react with these elements to form platinum group minerals right next to the recrystallized pyrite. But in the vein systems where you have a high water rock ratio, the palladium might be transported a considerable distance in the oxidized fluid until the fluid's buffered to a lower FO2 by reaction with magnetite, which would explain why these PGM are being deposited in these partially magnetized magnetite veins. So to sum up, the palladium was deposited with primary copper and gold in the primary hypogene mineralization from a magmatic fluid. It doesn't matter if that was a vapor or a brine. Palladium was probably transported as a bisulfide complex and precipitated with nickel in pyrite in solid solution. And then the PGMs didn't appear until the pyrite broke down by reacting with a later fluid. If you can find nickeliferous pyrite in one of these systems, that may be an indicator of PGE mineralization. And if you're prospecting in an area like this and you find some of these distal IOA veins, which are quite common in these systems, assay them for palladium, and if they're palladium rich, then you may have one of these systems that's got palladium in the hypogene, been remobilized and then trapped in the magnetite. And in the most potassic magmatic systems, you may see palladium-rich pyrite deposited or palladium deposited in other minerals in copper-poor, high-temperature inner zones that don't get sampled because they don't visibly contain copper or gold mineralization. And that's all that we have to say today. We want to thank the people at New Afton and the NSERC Engage Grant system for supporting this research.